Welcome to the wonderful world of physics. This is Physics 102b. We'll look at the last half of Chapter 18, that's sections 4, 5, and 6. We've already seen previously in this chapter how a charge moving through a magnetic field experiences a force. And so you can look at the picture here. Remember, there's the charge with its velocity vector. Here I've drawn it as a positive electric charge going through the magnetic field. And we learned the right-hand rule that shows that the force in this case is going into the page, and I've drawn that as an X. Now I want to think about a collection of charges moving in the same direction. So as I've written, a stream of charges, for example, a wire that is carrying a current. So it's going to have the same effect. It's going to be in the same direction as we learned with a single charge. Look at this picture that I've drawn. Here's a wire, and I've drawn the current going up and to the right, but I want you to think about, remember that it's actually a stream of negatively charged electrons going down and to the left. But we're going to think of it, as we use the right-hand rule, as the direction of positive current, going in the direction that a positive charge would go. So we'll use the right-hand rule, and just like the picture that's up and to the left of the single charge, the force on this wire is also going to be into the page. Whereas with a single charge, the force was given by that single charge times its speed times the magnetic field times sine theta. Here, when we have a collection of charges, this is the equation that the force equals the current times the length times the magnetic field times the sine of theta. Let's look at some examples in the back of the chapter. We'll start with number 28. It says a 50 centimeter long straight wire carries 2.5 amperes. It makes a 30-degree angle with a 0.30 Tesla magnetic field. The strength of the magnetic field on the wire, the strength of the magnetic force on the wire is what? And so we'll use this equation. Here I've drawn the picture, but force is current times length times magnetic field times sine theta, and we get 0.19 newtons. And as I've drawn it, it would go into the page. Question number 29. A straight conducting wire carries 0.25 amperes in the plus y direction, as you can see I've drawn. Find the magnetic field that results in a force per unit length on the wire of 0.2 Newton meters in the plus z direction. So we want to make our outstretched right hand go up. According to the picture that I've drawn, our thumb has to point out of the page, that's the plus z direction, and our fingers will curl in the left direction, so that's going to be in the negative x direction. We know that the current is 0.25 amperes, force per length is 0.2 newtons per meter. And so let's take this equation, F equals ILB sine theta, and we want to solve it for B, but I want to isolate force divided by length because that's a quantity that's given to us. So we'll say F over L equals IB sine theta. So B is F over L divided by I sine theta. Sine theta becomes 1, and you can plug in the values and get 0.80 Teslas in the negative x direction. Let's also look at number 58. It says a 7.7 centimeter length of straight wire runs horizontally along a north-south line. So there, I've drawn it with the compass directions along the north-south line. The wire carries a 3.45 ampere current flowing northward through a uniform 1.25 Tesla magnetic field directed vertically upward. So I've drawn the magnetic field coming out of the page. Find the magnitude and direction of the magnetic force on the wire. We can use the right-hand rule to find the direction of the force. Your thumb, when you use your right hand properly here, should point to the right, and that would be to the east. And we'll use the equation, force equals current times length times magnetic field times sine of theta, and you get 0.332 newtons. I'm now going to get into some applications of this. Let's look on the torque on a current loop. So here, this picture at the top, we have a rectangular wire loop with a current that's in a uniform magnetic field. And I've drawn the current going around counterclockwise. This rectangular wire loop has a length A and a width B, and the magnetic field is going straight up, as you can see in the diagram. I want to consider what are the forces on each side of the loop. We're going to use the right-hand rule. And let's start on the side that is on the right hand, where my marker is. And we're going to use our right-hand rule. And we can see, actually, we don't even need to use our right hand. The current is parallel to the magnetic field, and so there is no force. Also, on the left-hand side, the current is anti-parallel with a sine of 180 degrees coming out to 0, and so there is no magnetic force on the left and right sides. Let's look at the top and bottom sides. We're going to use the right-hand rule. And let's go to the top side first. I'm down here at the lower picture. And I'll use my right hand pointing in the direction of current. Magnetic field has my fingers curl upward on the page, and my thumb points into the page. So on that top side, there's a force pushing into the page. On the bottom side, the current's going in the opposite direction. So my right hand points to the right. Magnetic field makes my fingers curl upward, and my thumb comes out of the page. And so what we've got is this thing is going to be rotated. The top side is being pushed into the page, the bottom side is being pulled out of the page. The force on each of those sides is current times length times magnetic field times the sine of the angle, but at the moment, well, it's 90 degrees. And so that just becomes I times, now the length is lowercase a, and then times b. So the force on each of those sides is I times a times b. There's the picture again. There is a net torque that exists. Now there's no net force. Here I've written that the sum of the forces is 0 because they are equal and opposite. One force pushing in, the other force pulling out. So the forces cancel out, but the torques go in the same direction. Remember from last semester that torque equals force times the lever arm, which is the distance between the rotational axis and where that force is applied, times sine theta. All right, so let's think about the torque. It's helpful to look at this diagram at the middle of the page. At the top, the force going into the page is, as I showed on the last page, the current times A times magnetic field, B. The lever arm is, remember, the width of this loop, or I should say the height of the loop is lowercase b over, or it's lowercase b. And so the lever arm from the axis to where the force is being applied is lowercase b over 2. And the same goes for down below. So what you've got is the torque on the top part of the wire is IAB times lowercase b over 2. And then the torque on the bottom is the same, IAB times lowercase b over 2. And they go in the same direction, so they add. Now, when we clean that up, we get 1/2 IA lowercase bb plus 1/2 IA lowercase bb. Now, the bit that I've done in green, lowercase a times lowercase b, that's the area of the loop. So we can clean all this up and say that the net torque on this entire loop is IAB, so the current times the area times the magnetic field. And conceptually, that should make sense to us. We're going to get more torque. It seems reasonable that if we have more current, we're going to get more torque. The more area there is, we'll get more torque, and the greater the magnetic field, we'll also get more torque. Now, as it rotates, the sine theta aspect of the torque equation will kick in, and it'll decrease actually from whatever the torque that we just found is down to 0. In the previous example, as I was deriving it, I used a rectangular loop. It doesn't have to be a rectangle. I just did that because it keeps the geometry easy. But any loop will do that is in a plane that has some area A. It can be a coil that has multiple loops. And so let's take this circular coil here. The current goes in, it goes around and around and around many times and eventually comes out. The torque is going to be N times the current times the area times the magnetic field times sine theta, where N is the number of loops and theta is the angle between the magnetic field and a vector perpendicular to the loop plane. An application of this is an electric motor. An electric motor is used to turn electrical energy into mechanical energy. Here we have a magnetic field, a uniform magnetic field that is set up between two poles of magnets. And there we have a loop going through, so we have the current going in and then goes around and goes out. And as you saw in my previous derivation, it will have a current that runs through it continuously and keeps it rotating. Here we have an edge-on view of the magnetic field. There's the loop, the current going into the page at the top, the current going out of the page at the bottom, and then it'll cause this to spin. Example 1810 in the book, a washing machine motor. It says a washing machine motor has a 100-turn square coil 8 centimeters on a side in a 0.65 Tesla magnetic field. During the spin cycle, the coil carries 5.5 amperes. Find the maximum torque on the armature. Well, the maximum torque is going to be where the sine theta aspect of the equation goes to 1. And so we have torque equals the number of coils times the current times the area, which is 64 square centimeters, times the magnetic field, and we get a torque of 2.3 Newton meters. At the atomic level, each atom has what's called a magnetic moment. And let's look at this equation, thinking of it at the atomic level. So torque equals NIA. Now these are the properties of the coil when we're talking about a coil. And when we think about the atom, it deals with the current. So you think you have a moving electron and there is some area there. So those aspects are of the coil, whether we're talking about a machine, a washing machine motor, or an atom, it's what's called the magnetic moment, and we use the Greek letter mu for that. Its units are in amperes meters squared. The rest of the equation, the part I've set off in green, are external properties and the configuration. So that's the magnetic field that it's in times the sine of theta. So it's often useful to think about a current carrying coil in terms of its magnetic moment. Now, each atom has a magnetic moment, and therefore atoms in magnetic fields experience torques. And this is actually what leads to most magnetic properties of materials. The fact that the atoms that have magnetic moments are, experience torques in magnetic fields. And some medical applications, an MRI and an NMR, use these subatomic magnetic moments. So far in this chapter, you've seen a relationship between electricity and magnetism. You've seen that magnetic fields can affect moving charges. And now we'll get into section 18.5, the origin of magnetism. What we're going to see is that moving charges actually cause magnetic fields. the Danish physicist Hans Christian Ørsted, he observed that an electric current caused a compass needle to deflect. And so here we have our compass directions, and you lay down a compass, and of course it points north. But then if you run a current, and here I've drawn it going upward or out of the page, it would cause the needles to deflect and actually go around. It would show basically that the magnetic field lines go around that current. The current in a straight wire produces a magnetic field. It encircles the wire, and here we have, if the wire is coming out of the page, those magnetic field lines are going to go counterclockwise. If the wire is going into the page, they're going to go clockwise, and this calls for a new right-hand rule. And you can see down below the new right-hand rule to see which way those magnetic field lines are going to go. So we're going to imagine with our right hand, we're grabbing the wire, our thumb pointing in the direction of the current, and our fingers curl in the direction of that circular magnetic field. The magnitude of the magnetic field, a distance d from the wire, is given by this equation. So the magnetic field is, here's a new constant, mu naught times the current divided by 2 pi and the distance. Mu naught is called the permeability constant, or the permeability of free space. It is based on, mathematically, on epsilon naught, the permittivity constant that we've seen before, and related to the speed of light, and it's actually an exact value. It is 4 pi times 10 to the negative 7 Tesla's meters per second. And let's look at an example. Let's say we have a wire. I've drawn it to the right. The current goes to the right, and it's got a current of 5 amperes. And let's say we want to look at what is the magnetic field distance 10 or 1 centimeter away from the wire. Well, first let's use the right-hand rule to see what direction it's going. And I've only drawn in the plane of the paper, but if we grab the wire with our right hand above the wire, our fingers come out of the page. Below the wire, our fingers will curl into the page. So depending on whether we're above the wire or below the wire, that'll give the direction. But let's find the magnitude. Magnitude is mu naught, so 4 pi times 10 to the negative 7 times the current divided by 2 pi and the distance of 10 to the negative 2 meters. And so we work through that, and we get 10 to the negative 4 Teslas, which is actually greater than the Earth's magnetic field. So it would deflect a compass away from Earth's magnetic field. So far we've seen that a wire carrying a current is affected. It has a force on it by a magnetic field. Now we've seen that a wire carrying a current has a magnetic field that comes from it. Well, let's see what happens if we have a pair of parallel wires. I want to look at what their effect on each other are. So here you can see the picture that I've drawn. We have I1 and I2, and there is no external magnetic field. However, both of these currents is going to cause a magnetic field of their own. Let's put them at distance d apart from each other. And I want to first ask, what is the effect on I2 from I1? Well, I1 has a magnetic field, and so I use the right-hand rule to grab with my right hand I1, and we can see that in the vicinity of I2, meaning to the right, the magnetic field goes into the page. To the left of I1, it comes out of the page, but we're not concerned with that vicinity. And let's find the magnitude of the magnetic field. So B1, which is the magnetic field coming from wire 1, is mu naught I1 over 2 pi d. Now my original question was, what is the effect on I2? So let's now calculate the force of 1 acting on 2. And that equals I2 times the length of I2 times B caused by wire 1. So we have I2 LB1. And we're going to substitute in the line above. I just solved for B1. So we have I2L mu naught I1 over 2 pi d. So we get that the force of wire 1 acting on wire 2 is mu naught times the product of the currents times the length divided by 2 pi and their distance. Now, what is the direction of the force acting on I2? Well, we can use the right-hand rule, point our fingers up in the direction of I2. We then bend our fingers into the page, because that's the direction of the magnetic field caused by I1, and our thumb points to the left. So I1 is going to attract I2. We can also ask, what is the effect on I1 from I2? And we can go through the same procedure. We can find that the magnetic field caused by 2 is mu naught I2 2 pi, mu naught I2 over 2 pi d. Therefore, the force of 2 acting on 1 is I1 times L times B2. We plug all those in, and we get that the force acting on 2 is the same, the force of 2 acting on 1 is the same as the force of 1 acting on 2. And we can use the right-hand rule, apply it to current 1, point our outstretched hand up in the direction of I1. The magnetic field from I2 is going into the page, and so our thumb points to the right. And so what we're seeing is that wire 1 and wire 2 have an equal and opposite attractive force on each other. And Newton's third law, by the way, would have told us the same thing. Now, another thing you could do is do this with anti-parallel wires, meaning do the same thing but point I2 going downward. You can run through this entire exercise yourself and see that they will actually be repulsive to each other. The next thing I want to show you is the magnetic field that emanates from a circular coil. So you've just learned a right-hand rule that involves a straight wire. And now you think about applying that right-hand rule to different parts of this circular coil. So here this coil has a current running through it. And let's take right here where my marker is. And you can imagine grabbing that wire and your fingers curling around. And then let's go around the coil and grab it at different places. And you can see what the magnetic field is doing. And so before long, we can see that if we have this circular coil with a current going through it, the magnetic field will come, as it's drawn here, upward from the middle of the coil and go around and then come back up the middle on the inside. Now, at the center of the coil, there will be a magnetic field that points straight up. So let's go to the middle of the page. Here we have the coil of some radius, and the magnetic field, I've cut out all the clutter of all of the magnetic field lines going all around it. I'm just focusing on the collection of all of those, what's happening at the center of the coil. There is a magnetic field that is pointing perpendicular in that upward direction. And the magnitude of that magnetic field is going to be mu naught, the permeability constant, times n, which is the number of coils that go around, times the current divided by 2 times the radius. Now, this is a very specific equation. It only deals with the magnetic field at the very center point of the coil. The direction calls for a new right-hand rule. This is a pretty easy right-hand rule. You can see at the bottom of the page. If you curl your fingers in the direction that current is going, your thumb will point in the direction of the magnetic field. And here it draws it not as B, but simply as the magnetic moment, the mu vector. There's the equation again, that the magnetic field is mu naught times N times I divided by 2R. Let's look at an example. Let's say we have a coil that has a radius of 2 centimeters and a current of 20 amperes, and let's say it coils around many times for 100 turns. Then the magnetic field inside that coil is, we plug in all the values, there's permeability constant, 4 pi times 10 to the negative 7, times 100 times 20 amperes, divided by 2 times the radius, and we get 0.06 teslas. Now we'll compare that with the Earth's magnetic field at the surface is about 5 times 10 to the negative 5 teslas, so it's about 1,000 times stronger than Earth's magnetic field. Here is a more complete view of the magnetic field around a circular coil. In the previous example, we are just finding the magnetic field as it comes right in the center, so it comes upward in the center. But you can see all the field lines going all around, and it looks a lot like the field lines from a bar magnet. Now, let's take that coil, turn it on its side, and let's add more coils. As more coils are added, the interior magnetic field becomes more uniform and the exterior field weakens. The result is a nearly uniform magnetic field near the solenoid center. So this shape, these tight coils, are called a solenoid, and we get a nearly uniform magnetic field in the center. And this is the makings of an electromagnet. We can control magnetism when we turn on the current. It's a magnet, and turn off the current and it's not magnetic anymore. I also want you to see, if we have a single coil, the magnetic field coming from it, and think back when we're talking about electric vector lines, electric field lines, that the magnetic field lines look a lot like the electric field lines of an electric dipole. So any current loop is what's called a magnetic dipole. Thinking back to the solenoid, inside the solenoid we have a uniform magnetic field, and the magnetic field is given by mu naught times N, which is not how many turns, but how many turns per meter times the current. Outside the solenoid, it acts like a bar magnet, so the magnetic field is going to be particularly strong at the two different poles of the magnet. Notice that the magnetic field depends on the number of coils, but not on the size. All right, we'll finish off this chapter with section 18.6, magnetic materials. I want to talk about an aspect of some materials called ferromagnetism. I want you to remember back to each atom has a magnetic moment. It comes from the electrons in orbit around the atom, and also the electron has spin itself. And so essentially each atom is a little coil that has some magnetic moment. Whether a material is magnetic or not depends on its atomic properties, how many electrons occupy various subshells. The textbook goes a bit more into detail with it, but I won't go into that detail in this lecture. In iron, which is a ferromagnetic element, atomic magnetic moments tend to align with thousands of their neighbors to form what's called magnetic domains. Now, there are 5 ferromagnetic elements, and additionally there are compounds of those, but they are iron, nickel, cobalt, gadolinium, and dysprosium. So here's a diagram of these magnetic domains. The domains vary in size, but are typically about 1/10 of a millimeter across. Note that the magnetic moments of the neighboring domains don't generally align in the same direction. However, in ferromagnetic materials, an applied magnetic field can flip the domains into a common alignment so that the material acquires a net magnetic moment. So there we have a magnetic field, and they will align, and they become like little compasses, and together collectively they will make the material magnetic. You can try this at home. Take a nail or a paper clip and stroke it with a magnet. The stronger the magnet, the better. Hundreds of times in the same direction, and you will gradually get those magnetic moments aligned. And then, as you can see in the picture down below, the nail will become temporarily magnetized. Now, this state of aligned domains is a highly ordered state that is very subject um, to being brought into disorder. So if you drop the nail, you bang it on the table a few times, the domains will go into random alignment again. When we think about what we call permanent magnets, like a refrigerator magnet, these are materials that have been brought up to a high temperature. It's called the Curie temperature. It's almost like melting it. You're not turning it into a liquid, but I think of it as melting the domains. You're making the domains very flexible. So you bring it up to a high temperature. For iron, I think it's something like about 1,000 degrees Celsius. And you subject it to a magnetic field, as you can see in my picture in the middle here, and those domains will align. Then you bring it down to a lower temperature, and they will be frozen there. Now, even though we call it a permanent magnet, it's not really permanent, and even these magnets will lose their magnetism over time. That is the end of chapter 18. Have a great day.